Our next topic is 2-3 trees. So in this video, I'll be discussing about what are 2-3 trees, its properties we will learn, then how to insert or create a 2-3 tree, then deletion, then I'll do analysis. Then at last I can explain you why we need 2-3 trees, what is the use or what is the purpose of 2-3 trees. So let us start with what are 2-3 trees. Introduction to 2-3 trees. 2-3 trees are search trees. Like we have binary search tree. Binary search tree can contain one key and two children. Like this, we can have a value here like 20 and it can have two children. On this side you can have a smaller value and this can have larger value. So this is binary search tree. So same concept is extended for multiple keys or multiple children. Now this can have only two children because one key value. If you increase the number of keys, then the number of children can also increase. This one. Number of keys are 2 here, so it can have 3 children now. So this type of trees are basically called as multi-way search trees, and also they are called as M-way search tree. So what is M here? M is for multi-way, and the other meaning of M here is, see the degree of binary tree, if I say M is 2. If it is more than 2, it can be anything, so we say M. M, degree of a tree is M. So now I can say that 2-3 trees are search tree with a degree 3. Yes, they are with a degree 3. So 2-3 trees are multi-way search trees with a degree 3. Then next, 2-3 trees are balanced search trees, height balanced search trees. So there are height balanced search trees called as B trees. This B tree is a general concept. This is for any degree. But here the degree is 3. So you can call 2-3 trees are B trees of degree 3. Yes, this is also true. So what are the rules of B trees? How it can balance the height? So there are two rules that are applied on 2-3 trees also. Let us look at the rule. All leaf nodes should be at same level. This is the first rule. Then second rule is that every node must have at least half of the children. Half of the children means here degree is 3. 3 by 2 is seal value is 2 only. So yes, obviously we can have 2 children. So every node must have minimum 2 children. Yes, definitely we will have minimum 2 children here. But this is for general B tree. For any degree, rule is M by 2 children must be there. If degree is 5, then 5 by 2, 2.5. 2.5 seal value is 3. It must have 3 children. So this is about B tree. So we are learning B trees of degree 3. And 2-3 trees are famous. Mostly for learning about B trees, we study 2-3 tree. Through 2-3 tree we understand B trees also. Now let us look at the structure. See here, the degree of every node is 3. So every node can have 3 children. Left child, middle child, right child. Now you can name them like this, right? Left, middle and right child. When 3 children are possible, then 2 keys are possible. Then how those 2 keys should be? K1 should be less than K2. So it means the keys inside a node must be sorted. This is the first point about the structure. Then second thing, if you check the left child, that is left child, so whatever the keys present here, all the keys that must be less than key 1, right? And if you look at the keys inside N, then all the keys should be greater than key 2. Means key 2 should be less than all the keys present here. So I'm calling it as N. And what about M? M should have the keys, this node should have the keys that should be greater than K1 and less than K2. So M should be greater than K1 and less than K2. That's how. These are the conditions, how the keys must be arranged. So this is a simple thing. The keys must be arranged in the sorted order. And here you will find all the keys that are greater than K1 and less than K2. And these are all less than K1. Likewise. Then, and one more important thing, as this is a search tree, it cannot have duplicates. We cannot have duplicate elements, right? If you try to insert, then if it's already there, we don't insert it. Now let us see how to insert and how to create a 2-3 tree. So I'll take some keys and I will show you how to insert, and I will be creating it, right, by inserting in the elements one by one. So let us start creation. I have taken set of keys here. So I'll show you how to create a 2-3 tree by inserting these keys one by one. As I already told you that all leaf nodes must be at same level. So let us see how that is managed, right? And how height is balanced. Let us see. Let us start inserting. So first of all, I will insert 20. So for that, create a node. This is the root node. Okay, right now this is the only node. So we have root node 20. So 20 I have inserted. Inserted 20. Create a first node and insert 20. Then next, here only I will insert 30. Just watch this one, right? So 30 comes here only. It comes after 20. So 30 is also inserted. So I will draw a line here separating them. Now I have two keys in a single node. 20 and 30 is over. Now let us insert 40. So here I will write insert 40. Now in this one I will insert 40. So watch this now. This is important. So if you understand this step, then everything is perfect. 20 and 30 are there. 40 comes after 30, but there is no space, right? There is no space. No space means degree is 3, keys are 2 only. So 2 keys I have filled. Just now I have shown you the structure that key 1 and key 2. 2 keys are there. There is no space for key 40. Then what to do? Split this node. So if it is filled and there is no space for the new node, then split the node. Okay, split the node. So I will create 2 nodes. We have 20, 30 and 40 is not inserted, but consider that 40 also. So including that 40, if you see there are 3 keys now. So out of that, 1 key on the left hand side, 1 key on the right hand side, then 30 is remaining. That goes in another node as a parent. So 30 will come here. And this is the left child for 30. This is the right child for 30, or middle child. This is the middle child. There is another key is not there. So otherwise we will have a right child also, right? So left child and middle child. So we have space empty here, and also this is empty. So this is the split. So when I have splitted, how many nodes I created? 2 nodes I created. Until now I have inserted up to 40. So how many splits happened? See, this is the first split, and 2 new nodes are created in the split. And so this is insertion. Now one important thing, we have seen binary search tree. Binary search tree grows downwards, right? We find where the element should come and we will add it as a leaf node. So it grows downwards. But here it is growing upwards. See, already this node was there. So we have added this node above this one, So 2-3 trees or B tree, they grow upwards, right? That's how they maintain themselves balanced. So the procedure for insertion is this one, so that it balances the height always. Now next I have to insert more keys. Now let us insert 50. So here I will say insert 50. So in this one I have to insert 50. So I will draw this one once again. On this side we have 20 and 40. So I'll fill the keys now. 10, 30, that is 20, and this is 40. Now 50. Check here how to insert. See, this is the root. So I'm not marking it every time. So this is the root. We can understand that. 50. Check here. 50 is greater than 30. And next key is not there. So it should be in this node only. Go to this node. This is 40. 50 must be next. So search for 50 first of all. It's not there. That is vacant. So fill 50 here. Okay. This is perfect. So I don't have to do anything. Simply the key is inserted. Now next 60. So I'll include 60 also in the same step I will show you. Now 60, where it should come. Check here. Search for 60 first of all. 60 is greater than 30. Next, there is no key. So check in this child. Right? 60 is greater than 40. 60 is greater than 50. And that's all. This is over. So there is no space here. Actually, it should come here. But there is no space. 60 should come here. There is no space. Then what to do? When there is no space, just now we have done something here. Same thing. That's we will split. So take this root as it is. Then this node is 20. Right? And this node, we are going to split this node. Split this node. Right? So split this one. So how to split? 40 on this side and 60 on that side. The middle element 50 will go in the root, in the parent. Right? Here parent is root only. So it will go there. So 50 will go here, and this was already 30. So let it be as it is. I don't have to create a separate node for 50 because already the node was there in the parent and the blank space was there. So I have stored 50 there. So this is how 60 is inserted. Insertion of 50 was easy, directly we inserted. Insertion of 60 caused a split, one more split. How many new nodes are created? Only one new node is created because the parent was already there and 50 got a place there. Now I have to insert more keys, right? Next is 10 and 15. This I am going to insert. So here I will do insert 10. So for inserting 10, so first of all I will draw the same thing as it is there. Insert 10. 10, where it should come? 10 is, start searching for 10. 10 is less than 30. Go to the left child. Then 10 is less than 20. So it should be here. So what to do with 20? 20 you shift it there. Is there any space? Yes, the space is there. So shift 20 there and insert 10 here. Okay. No split required. Next. 15. So I will insert it in this structure only. Here only I will insert 15. Where 15 should be? 15 is less than 30 and greater than 10 and less than 20. So it should come in between. But there is no space. Actually this node should have 10, 15 and 20. But there is no space. Then do what? Split. So let us do it. So here I am drawing separately. Right? So split. So splitting I will get two nodes. 10 on this side and 20 on this side. See, considering 15 together I am splitting. 15 should go up. 15 should go up. So 15 will come here. Okay. Then the rest of the nodes, here I have a 40 and here I have 60. And in the root already we have 30 and 50. So this 50 was pointing on this one and this middle child is this one. Now this left child we have split it. There is no space for 15. Just now we have done it for 50. 50 went up and there was a free space. There is no free space for 15. Then what to do? Split that root also. So if we split, then we get one more node here. Okay, one more node and one node as a parent. One node as a parent. So what are the keys? 15, 30 and 50. So 15 will be on this side, 50 will be on that side and the root will contain 30. Yes. Then this will point on this one, this will point on this one. Now the new keys that we got, 15, less than 15, greater than 15, this is 20. That is the tree structure. So this insertion of 15 has caused two splits. One split here, right? There was no space. So we have splitted this. Then 15 went up in the root. So again, this is also split. So two splits are caused. So total, if you count, so far I have done 4 splits, right? 4 splits. And in this split, how many nodes are created? This is one new node and this is another new node. So 2 new nodes are created in this one. 2 new nodes and 2 splits are done. So this is one of the criteria for analysis. Now you can take this one. If you are doing paperwork, do this one and you create a tree up to here by yourself once, then you can always remember it. Just watching will not help you. Take the keys, right? You do it by yourself. Then I have few more keys remaining, that is 70, 80. I will fill them. Okay. So just take up to here. I will remove everything and I will redraw it here. Then I will insert 70 and 80. So you can take a snapshot for this one. All the insertion I have shown you. This is the first one. And for this is the result. For this is the result. For this is the result. So final tree is that one. Now I will draw that one here and we will continue. So this is the tree we have up to 15. Now next is 70. Where 70 should come? 70 is greater than 30, greater than 50, greater than 60. 70 comes here. The next key is 80. Where 80 should come? 80 is greater than all this. It should come after 70. But there is no space. Then split. So create one more node. Right. Now including this 60, 70 and 80 also. So 80 will go there. And the 70, that is middle element, will go up and this will be a right child. That's all. All the keys are inserted. Now one more thing. I will insert one more key, that is 90. So 90 is inserted here. A 2-3 tree is formed. So this is the approach for creating a 2-3 tree by inserting the keys one by one. So you have seen that it was growing upwards. Same method we follow for B trees also, B plus trees also. Now next, let us learn deletion. For deletion, I'll use the same tree, 2, 3 tree. From this, I will select the keys and I'll show you how to delete them. So let us look at the cases in this one. So first case, let us delete case 1. Okay. So I will not be mentioning here. You can note down the cases. So case 1. I want to delete 90. Delete 90. Case 1. Watch it here. Search for 90. 90 is greater than 30. There is no key here. So it must be in this middle node. Then it is greater than 50, greater than 70. So it must be in the right child. So it's greater than 80. Yes, we found. 90 is found. Then delete it. So okay. 90 is gone. 90 is deleted. Any changes we have to do? No, no changes. So this is the case 1. We have searched for a key and the key was in the leaf. It is simply deleted and there is no effect upon the 2, 3 tree or a tree after deletion. This is the first case. Simply delete the key. Then case 2. Case 2. I am deleting 80. Delete 80. Let us search for 80. 80 is greater than this, greater than this, greater than this. So come on this side. Yes, 80 is found. Delete 80. 80 is gone. See, we have deleted 80. Already we have deleted 90. So I'm writing them outside. Now 80 is gone. When 80 is gone, then what this node is doing? This node has become vacant. We should not have empty nodes. Then what to do? Merge this with sibling. Either the left sibling or right sibling. So how to merge? See, at the time of insertion we were splitting. At the time of deletion we will merge. Join it. So join these two. So joining these two, remove this node which has become vacant. So just leave it and bring 70 here in this one. This is merging. So you bring the key from the parent and join these two nodes. So I'll show it separately here. See, if suppose you have 10 here and 30 here and 20 here. Watch this step carefully. This will give you the idea. Merging means what? Suppose you are deleting 30. Then you have to join these two nodes. Join these two nodes, right? 10 is already there. Then copy that key value also here. Copy that key also here. That key. So this key is also gone. So as this one is vacant, so this becomes vacant. So you have to delete this node also. So when you are deleting 30, you have to delete this node as well as this node. But here we don't have to delete the node. We don't have to delete the node because already one more key is there. So just we have copied that. So this was case 2. Now I will show you case 2 once again for another key, that is 60. So I will write down the things back again. This was 70 and this is 50, 80. This was 80. Okay, 90 is already gone. So now delete 60. So if you are deleting 60, search for 60. 60 is found here. Delete 60. Now this node is vacant. Then what to do? You can join with either left sibling or right sibling. Anyone you can join. Anyone. So let us join with right sibling. If you join with right sibling, then 70 will come down and 80. They both together will be in this node. So it will be 70 and 80 and this node is gone, right? This node is gone and 70 is also gone. It looks like this. So this node is gone. Now one more thing. I said that this can be merged with right sibling as well as left sibling. Let us do it with the left sibling. Let us do it. So I will write down 70 and 80 as it is. Now deleting 60. So this should be merged, left sibling. So 50 should come down. 50 should come down. So you can bring it into this node and this node is deleted. Then what about this? So you have to shift 70 also. And instead of right child, this becomes a middle child. These are the changes you have to do. So either you merge with left sibling or right sibling. So here merging with the right sibling was better, right? It was better. But if you don't have right sibling, then you have to go with the left sibling. So you have an option. Now we will see next case. So for that, I will draw the tree back again as it is, then I will do it. Now next case, I want to delete 60. Let us delete 60. Search for 60 and delete it. So 60 is gone. 60 is gone. This node is vacant. So you remember what we were doing? We were merging. That I have shown you as case 2, right? So we were merging. But before merging, there is one option. There's one option. Let us see. Can we borrow a key here? Let us check on the left hand side. This is having only one key. It cannot share it with you. Then let us check on the right side. Yes, it is having two keys. It can share one key with us. So let us borrow a key. So borrowing, we have to borrow it via parent. So 70 should come this side and 80 should move into root and 90 should be shifted here. This is borrowing. So third case I have shown you, that is borrow. So far we have seen the cases. Simply delete the node, then delete and merge, and the third one is borrow. So actually this should be the first step. Borrowing should be the first step. If borrowing is not possible, then you can merge. So I have shown you borrowing at the last. So let me show you borrow here once again. See, this was having two keys and here is one key. Let us say 10 and this is 20 and 30 and 40. Suppose 10 is gone. So if 10 is gone, then who should take its place? 20 should come here and 30 should move up. So this is how you can borrow, right? 30 should go. So I'll redraw it in the next level, that is 20 and this was 10. So if 10 is gone, then here comes 30 and here it will be 20 and here it will be 40. So this is how borrowing can done. And borrowing is done via root, via parent. This is done via parent. So these are the cases. Now, three things, either simply delete it or borrow it or merge it. So already I have deleted few keys. Now let us delete few more and see how we can work out with them. Suppose I want to delete 20. If 20 is gone, so check, can you borrow? There is no key on this left hand side. Then do what? Merge. If I merge, then I should take a single node, right? I'll remove this. I should have 10 and 15 here. Then what about this? This is empty. When this is empty, can we borrow from here? Let us delete 20. So if I have to delete 20, search for 20. So 20 is found here. Then delete it. If this is deleted, first check, can you borrow something? Borrow from the left sibling. There is nothing to share. It cannot give a key. Then do what? Merge. So first try to borrow. If you cannot borrow, then merge. Okay, merge it. So I'll bring this 15 here. Okay, 15 is here. And this node is gone. Okay, perfect. Then what about this? This became vacant. So it is just like cascading. If you delete one and you have merged one, then again you may have to check again the parent. So again now you have an option, borrow or merge. So can you borrow? Yes, from the right side you can borrow. So without borrowing, just check, can you merge? Merge means what? You have to combine this, 30 should be come down. So already two keys are there, you cannot bring 30 here. So yes, it is having more number of keys, so you cannot merge, but you can borrow. So borrow from there. So borrow from where? Right child. So how it should be done? See, this is the first key. This can go up. Okay, 50 goes up. Then what about 30? 30 comes here. Then when 50 is gone means what about its child? So that child will come on this side. It will come on this side. So you have to modify these links. So 40 came here. Then what about that? You shift them. So here you bring 70. Actually I am redrawing. Okay, just we have to shift these. So remove this 90 and bring 80 here. So these are the changes. I have made multiple changes, so you have to watch it once again and watch it slowly, then you can understand everything. So I have borrowed a key from right child. So 50 came here, 30 came here. So this was perfect. Then what about 40? 40 was a left child, it became a right child here. Then 80 was here, so I have shifted these values because we cannot have first location empty, first key is not there, second key is there. So we cannot have like this, so I just shifted them. So this 80, 70, 90 were there, so I have shifted them here, nothing else. I have just shifted. So this is how deletion is done. Now one more key I will delete, one more key from this one. I want to delete 50. 50 is gone. Who will take its place? So if you remember in binary search trees, when you delete any node, its in-order predecessor or in-order successor will take its place. In binary search tree we have learned this. So same thing we have to do. See, till now I was showing only deletion of leaf nodes, but non-leaf nodes I am showing you. I am deleting 50. 50 is gone. Then who should take its place? Either 40 should take its place or 70 should take its place. Watch this. This will have multiple steps. Just watch this one. So I want to send 40. Okay, 40 goes here. Then what about this node? This is vacant. So if this is vacant, borrow. So bring 30 here and send 15 in the root. So we have borrowed via parent, right? Via parent in the right direction. So this is changed. Now let us delete one more. I want to delete 40 once again. Root. So delete 40. 40 is gone. Who will take its place? In order predecessor, in order successor. So what is that in order predecessor? Means go to left, then rightmost key. Or here go to right and leftmost key. So here I will send 30 up. So 30 has gone up. This is vacant. Then can we borrow from this child? No. Then do what? Merge. So I will use this node. 10 and 15 are merged. Then what about this? This is empty. This is empty. Can we borrow from there? No, we cannot borrow. Then merge these also. Merge these also. So what we will do? I will write one node. Okay. And this side was this one. So in this 30 will come down and this 80 I will show it here. 80 is here. Then this is middle node and this is right node. So this node is also gone and this is also deleted. This is how it looks like. Again, you have to watch this slowly, right? Step by step you watch it, how I have worked. Right? This one once again, play it at a slow speed and watch it. So this is how deletion is done. So in deletion, primarily there were three cases. Search for a key and simply delete. It is not at all affecting a tree. And second one, delete and merge. Or next is delete and borrow. If you cannot borrow, then merge. So I have shown you all cases. Like I have grown the tree, then I have reduced the tree. Okay. So that's all about creation and deletion of keys from 2-3 tree. We will do some analysis, then I will tell you why or how 2-3 trees are used. For analysis, I have taken two examples of 2-3 trees. If you see this example, this is having minimum number of nodes and minimum number of keys. And this example is having maximum number of nodes and maximum number of keys for a given height. Height I have taken as 2, that is 0, 1, 2, and this is also height 2. So within height 2, we have minimum keys and minimum nodes, and here also maximum keys and maximum nodes. Now we are interested in knowing in a 2-3 tree of height h, minimum how many nodes are possible, maximum how many nodes are possible. So let us see. If you observe this, in height 2, if you count the nodes, first level, right, at height 0, there is only one node, and here 2 nodes, and here 4 nodes. So it's looking like a binary tree. So the formulas for binary tree can work here, yes. So if you observe minimum number of nodes, n equals first level 1 node, then next level 2 nodes, then next is 2 square. So this how it will be going on, increasing up to given height. So it will be 2 power h plus 1 minus 1 number of nodes. So minimum number of nodes are 2 power h plus 1 minus 1. Then let us check maximum number of nodes. Now in this example, first level, right, we say this as level. So level 1 node is there. Then in this level 3 nodes are there. Then in this level 3 square 9 nodes are there. So 3 square. So up to any given height there will be 3 power h maximum number of nodes. So total how many nodes are there? Total 3 power h plus 1 minus 1 by 3 minus 1. So if you know the sum of the terms of GP series, this is the formula. Formula for sum of the terms of GP. This is geometric progression. Every time the term is multiplied by 3 to get the next term. So that's how 3 is a common ratio. So this is the formula, right? You can refer the formula, you can search it and find out in Google sum of the terms of GP series. So this is how maximum number of nodes are possible. So n is equals to 3 power h plus 1 minus 1 by 3 minus 1. Now these are minimum nodes, these are maximum nodes. Now actually degree of this is 3. 2 are the number of keys. Degree is a 3, but here we got a 2. So that is 2 is half of that 3. That is seal value of 3. So if you remember, 3 by 2 seal value is what? 2. So that's how we got 2 here. Means if this is not a 3, if this is any other thing, then it will be divided by 2 and the seal value. That many nodes you will have, right? For any other degree. We are analyzing only for degree 3, but for any other degree, that's how it will be. Half of the degree. This is half of the degree. Now, I have the minimum nodes and maximum nodes. Now, from this formula, I can find out maximum height. So, from this formula, if I convert h equal to how much? Send this minus 1 here. So, this will be n minus 1. And bring this base 2 here. So, if you bring it here, it will be log base 2. And that plus 1 comes here, minus 1. So, this is logarithmic. So, big O of log n base 2, I can say. So, maximum height is asymptotically, it is log n base 2. Now, similarly, from this formula, that is maximum nodes, I can find out minimum height. Minimum height is, if I convert this, if I take out height, this will be n into 3 minus 1. I am keeping it as 3 minus 1. Actually, it is 2. So, 3 minus 1 because the degree minus 1. So, I am keeping it as 3 minus 1 only. This minus 1 comes this side, so it becomes plus 1. Then bring this 3, base 3 here. So, it will be log base 3 and this whole thing. And this plus 1 comes here, minus 1. So, this is log base 3 n big O. So, this is also log, this is also log. So, now from this we can say that the minimum height of 2, 3 tree is log n, as well as maximum height is also log n. Only base is difference, but it is logarithmic. So, this is the proof that height of a 2, 3 tree, or in general height of a B tree, is always log n. So, this is the conclusion of this analysis. So, that's all about the analysis. We found the maximum minimum nodes and maximum minimum height. Alright. Now, the last thing is where this 2, 3 trees are useful. Actually, it's a B tree or B plus tree. B tree or B plus tree. These are used in databases, DBMS softwares, right? Like softwares like Oracle, SQL Server or MySQL. These softwares internally uses these things, right? If you are developing such a software, then you have to use this one. So these are useful there. And this 2, 3 tree is a type of B tree. It's a type of B tree. For studying B tree, 2, 3 tree is used as an example, right? Because if you take a bigger degree or larger size degree, it is very complex to do some board work or understand the concept. So it is understood at a small level by taking only degree 3. This is one reason. Then why B plus trees are used in databases? Because at once when we access a node, we can get more than one values at once. If it is a binary search tree, then each node can have just one value. So when you are fetching a node, you get only one value. But here in one single node, more than one values are there. So once you have reached at any node, you can access two values. So when you have reached a particular node, suppose here, then when you are accessing this one, then next address is the next value. So you can easily access it. So if you have the idea about direct accessing and indirect accessing. So in a node, these values, both of them can be accessed using direct access method. That is in a single step. And if you want to access this node, then from here you will be taking an address and going there. So that is indirect access. So going to the next node is indirect access. Then within that same node, it's direct access. So the benefit is that in direct access, you can get multiple values at once. So it is little faster than using binary search tree. And one last point. If you are using binary search tree for these keys, then the height of a tree will be very big. But here, the height is smaller one. So if you talk about height, this height is smaller than binary search. So that's all in this video. We have learned about 2, 3 trees. The topic is 2, 3, 4 trees. Already in the previous video, we have learned about 2, 3 trees. If you did not watch that video, I suggest you must watch it for understanding this one, because a lot of concept already we have discussed in the previous video. If you have skipped it, go and watch it, then you can understand. Here I will show you a few things that are related to 2, 3, 4 trees. Now let us see what is 2, 3, 4 tree. It's a B tree of degree 4. So what is a B tree? Everything I have explained in the previous video. B tree is a multi-way search tree, and it is a height balanced multi-way search tree. So how it will balance the height? By imposing two conditions. All leaf at same level. That's one of the condition. Then every node must have 4 by 2 degree by 2 number of children, that is seal value. So this is 4 by 2, 2 children must be there. Yes, obviously every node will have definitely 2 children. Now when the degree is 4, then how the node looks like? Let us see. Degree is 4 means 4 children are possible, so 3 keys are possible. So here 3 spaces are there for the keys, and 2 more children can be there. But here there are 2 children, so only 1 key, or 1 key there are 2 children. This is first possibility. Second, 2 keys are there, 3 children are there, and then 3 keys and 4 children are there. So that's why degree is 4, but minimum there can be 2 children or 3 children or 4 children. So that's why it is called as 2, 3, 4 tree. So every node can have either 1 key or 2 key or 3 keys. Now how to create a B tree? We have already seen it in 2, 3 trees, and deletion also I told you. Here there is some differences there, so that we have to see. So let us take some keys and create a 2, 3, 4 tree. So here I have keys. Let us create a 2, 3, 4 tree. So let us insert all these keys one by one. So first step is I will insert 10. First step. So for that, create a node with a degree 4. So 3 keys are possible. First key 10 is inserted. The next, insert 20. Yes, 20 can be inserted here. 30 is inserted here. So this is full now. Now next step I will show you here. Insert 40. If I insert 40, now this is the thing that we have to learn. New thing. 10, 20, 30, 40, there is no space. When there is no space, what we were doing in 2, 3 tree, we have learned already there. So here just I am showing it for degree 4. So when you have one more key, there is no space, then you have to split. So let us split this one. So here we get one node and another node. So let us make that node as root node. Okay, this node as root node. So now along with these 3 keys, we have to consider 40 also, that is 4th key also. Then out of this we have to split, and we know very well that one of the key will go in the root. But how many will go on left side and right side? Here you have even number of keys. That is the point. That is the difference here compared to 2, 3 trees. So when you have even number of keys for splitting, then either you can be left biased or right biased. So you can have more keys on left side or you can have more keys on right side, because you cannot divide them uniformly. That's it. So you can have left bias splitting or right bias splitting. This is the new thing we are learning in 2, 3, 4 trees. So here I will do one thing. I'll take 10 here and 20 in the root, right? And I will take 2 keys on this side, 30 and 40. So I made it right biased. I have made it right bias. So this is the left child, this is the right child. So splitting is done. 1 key on that side, 2 keys on this side. Because I have taken some keys based on that, I want to show you more splitting. So that's the reason I am taking 2 on this side. Or else you can take 2 this side and 1 that side. So in that case, 20 will be here, 30 will go here, and 40 will be at this place. So this is first splitting. Now let us continue inserting other keys. So I have finished till 40. Now next is insert 50. So let us check. I will copy the same thing, right? So this is 20, and on this side we have 10, and this is 30 and 40. Now inserting 50. 50 should come at this place. 50 is greater than 20 and greater than 30 and 40, so it comes here. Then next I will continue inserting 60 also here. There is no place for 60. There is no place that split. So I will take small pictures now because I need more space. So split this one once again. So this is splitted. Now here we already had 10. Now this is being splitted. So we got one more node, and here we had 20 already. This was pointing here. Now when this is splitted, 30 on this side, 40 goes up, and 50 and 60 in this node. Now this is the second child and this is the third child. So this is the result of splitting when we were inserting 60. So you can count the number of splits also, first split and the second split. First split was at 40 and second split is at 60. And here I got 2 extra nodes and here we got just 1 extra node, right? Now next 70 and 80. So here I will say insert 70. So in this I will continue. So this is 20 and 40. And on this side we have 10 and here we have 30, right? And here we have 50 and 60. So insert 70, 70 comes here. Then insert 80 also. So there is no space for 80. So again split it. So here we got, this is one node, second node, and this third node, it will split further. So this was 10 as it is, 30 as it is, 20, and this was pointing here, 40, this was pointing here. Now this is splitted, so 50 comes here, 60 goes up, and these are 70 and 80. So this will be pointing here. Now this is the result. So one split, one extra node when we are inserting 80. Now remaining nodes I have 90 and 100 and 110. So next let us insert 90 and 100 and see it here. If I insert 90, I will directly insert it here only. So 90 will be inserted here. So actually this is the result of this one, but there is no space, so I will show it here only. So insert 90 as well as 100. So 90 already I have inserted. When I try to insert 100, 100 comes here and there is no space here. When there is no space, again split. So here I will show you. Okay. So this 10 is as it is, 30 is as it is, and this is 50 as it is. Then here we have to split. We have to split this one. 70, 80, 90, 100. So there is no space, split. So 70 remains on this side and here will be 90 and 100. Then who goes up? 80. So this is the node which is already having 20 and 40 and 60, 40 and 60. So when 80 comes up, there is no space. So this 80 goes up, there is no space. Then again split. So again if I split, then on the top I should have one more node, and 40, as we are making it right bias, so 40 goes up, and for this 60 and 80 I should have one more node here. So this is 60 and 80, right? So 40 has went up. So this is the left child of 40, this is the right child of 40, and this was the left child of 20 already and the right child of 20 already. Now this node is splitted, so 60 is left and this is the second, and this is 80 is right, third child. So this is how the tree looks like. So 2 levels of splitting is done. So this you are already familiar, and so just you can take the snapshot and take these keys and do it by yourself. Do it by yourself. If you do it by yourself once, then you can remember it. Anytime you can do it, and also you can easily program it also. So just take a snapshot of this one. So that's it. This is the insertion. Now I'll show you a little bit about deletion. It is same as 233, but once more I will delete few keys and I will show you. Okay. I will copy that tree here, then I will show you how to delete. Let us see how to delete keys from 234 trees. The procedure is same as 233, but as an example, let us do it once here. Already I have shown you cases in 233, same cases applies here. So I'll just repeat those cases by selecting some keys here. I want to delete 100. So first of all, search for 100. 100 is greater than 40. So go to the right side, is greater found. Then delete. So after deletion, at least there must be one key or 2 children. 2 children must be there. But actually these are not leaf nodes. They don't have children. But there is a possibility of 2 children. One key is there, means 2 children are possible. Yes. Then this is deleted. So I'll put back that 100 once again. Now, second example. I want to delete 70. So search for 70. 70 is deleted. 70 is deleted. This node became empty. So what to do? Replace it by borrowing the key. So from this side we cannot borrow. From that side we can borrow. So we can bring 80 here and 90 at this place. And this becomes 100. Okay, means 100 is shifted here. This is how you can delete that 70. Now next case, I want to delete 30. So search for 30. 30 is less than this, 30 is greater than 20. Go to this side, yes, 30 is found. So delete this one. Now this became empty. So borrow a key. Can we borrow a key? There is no key available here. Then do what? Merge. Okay, 20 is brought here and it is merged with this one. So this is in this node. Now this became empty. This became empty means try to borrow. Can we borrow? Yes, we can borrow from that child. So how to borrow this one? This 60 goes here. So this will become 60 and 40 comes here. This is 40. Then this left child of 60, the left child of 60 will come on this side. So this will be 50, right? So 60 is there. So 50 is removed. So what we do now, we have to shift these, slide these. 90 comes here. So this is 80 and this is 100. So basically these are shifted. So I'm removing this node. Okay, I'm removing this one. So when this became empty, there was a possibility of borrowing. So we have borrowed from the sibling via parent, right? This is over. Now the last one, last example. I want to delete 80. So let us delete 80. 80 is gone. Now this is empty. Can you borrow from sibling? No. Then do what? Merge. When you are merging, so 90 and 100 comes here in a single node. So this node is gone. And this is empty. Now this node is empty. So do what? Borrow. Can you borrow from here? No, it cannot be borrowed because there is only one key on this side, right? If two keys are there, then you can borrow. There is only one key. Then do what? Merge that one also. So merge these two together. So bring that one here, 60. So this will be the right child of 60 and this is merged. See, these two are merged. So this node is not there. So where that key will come? In one node. So this is also gone. This is how the result after deletion. So I have deleted all the keys, various keys I have deleted one by one. So this you need to do practice, right? I have done the board work. So watch it slowly at a slow speed or give pauses and do it by yourself. What all I am doing, you have to observe it and do it by yourself. If you do it by yourself using pen and paper, then you remember it. Just watching will not help you. You can't remember this one. You can't again put it back on paper. So you do it right now. Pause this one and check every step and do it by yourself. So that's all I have to tell about 2, 3, 4 trees. I have shown you what are 2, 3, 4 trees, then insertion and creation, then also I have deleted by taking all possible cases. And if you do the analysis, it is similar to 2, 3 tree, so you can do the analysis by yourself. So this height of this one will also be always log n because this is a B tree of degree 4. So always log n. So that's all about this 2, 3, 4 trees. So that's all in this video. Now the topic in this video is red-black trees. I am going to explain the properties of red-black trees and how to insert and how to generate a red-black tree. These are the two things we will learn in this video. Properties and creation of red-black tree. So let us look at the properties. See, first of all, red-black tree is a height balanced binary search tree. So it's a binary search tree. You have already studied about binary search tree. There is a topic available. And also we have studied about AVL trees that are height balanced binary search tree. So this is also height balanced binary search tree. If you remember, in AVL tree, we will try to balance the height by performing rotations if any balance factor is violated. Similar thing we do here, we perform rotations if red-black conditions are violated. So it's more similar to AVL tree. But this idea of red-black tree originates from 2, 3, 4 trees. So we already have a topic called 2, 3, 4 trees. If you are perfect in that one, if you have practiced that one, then this is nothing. Red-black tree is very, very simple if you have the clear idea of 2, 3, 4 trees. And even I am going to relate it with red-black tree with 2, 3, 4 tree in the coming video. Now let us look at other property. Every node is either red or black. So nodes will have color that are red or black. Some people take edges as color or nodes as color. So we'll follow nodes as color. Nodes are either red or black. That's why it is called as red-black tree. Then root of a tree is always black. So root of a tree is always black. So here you can see I have taken an example of red-black tree. This root is black. So root of a tree, that is the main node, the first node, is always black. Then nulls are also taken as black. See here, after this node, there's a leaf node. So this doesn't have any child. So but null are there. So if you know the linked representation of a binary tree, if you take a node will have a key value, and if it is a leaf node, then these values will be null. These pointers will be null. So those nulls are also treated as black. So I am highlighting them as black here. So nulls are also black. Now next thing, number of blacks on the paths from root to leaf are same. Let us count black nodes. 1, 2, 3. These are 3. 1, 2, and go along this path. 3. 1, 2, 3. Let us go in this direction. 1, 2, and this is 3. 1, 2, and this is 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So in every path you go, you should have same number of black nodes. That's the another property. Then no two consecutive red nodes should be there, right? Like this is red and this is also red, it should not be there. Like this is red, then this should not be red. So no two consecutive reds. It means if there is any red node, then its parent will also be black and the child will also be black, definitely. So for any node, parent and child of red are black. Then next, newly inserted node. When you are inserting a new node, always it is inserted as a red node. Then next and the last thing is the height of a red black tree is minimum log n, maximum double of log n, that is 2 log n. So if you remember the height of a binary tree, minimum it can be log n, maximum it can be n. But when you are trying to make it height balance in AVL tree, it is 1.44 into log n. 1.44 into log n. Now red black tree is 2 into log n. So it is little relaxing compared to AVL tree. So we can say that AVL tree is more strict, but red black tree is not that much strict. So it allows the height to grow up to 2 into log n. So the maximum height of red black tree is 2 log n. By looking at all these properties, you may be worried how to remember this. Do I have to remember all these? If you're writing academic exam, then you have to remember these, right? And if you're facing interview also, they may ask questions randomly from these properties. But do you have to remember these always? No, you don't have to remember them. If you remember the tree creation process that I'm going to show you next, that will help you recall all these points, right? So you don't have to spend special time in memorizing them. If you know how to create, you can remember them. So let us take few keys and create a red black tree. So I'll show you the insertion process, which is more similar to a BST, that is binary search tree, plus AVL tree, that is height balance, because rotations are also there. Let us look at tree creation. Here I have taken some keys. Let us create a red black tree by inserting each key one by one. So let us start. The first key that I have is 10. I have to insert 10. So remember, the insertion will be done just like binary search tree, just like binary search tree. So first key is 10. So always a newly inserted node will be red node, right? So this is inserting 10. Insert 10. I have inserted 10. But this is the first node and it is a root node. So you remember, root node must be black node. So I should change this color and make it as black node. So I'll change it to black. So this is 10. 10 is inserted. Now next key, 20. So here I will continue, insert 20. So this is already 10. So where 20 should come? 20 is greater than 10, so it should come on the right hand side. So 20 is this one. Now when you are inserting a new node, it should be a red node and its parent is black, then no problem. No problem with the balancing the height. You don't have to do anything. It's perfect. Now next key is 30. 30. So where 30 should come? Here I will say insert 30. Inserting 30. Right now this is 10 and its child is 20. This is 20, which is red now. And 30, where it should come? 30 is greater than 10 and greater than 20. So 30 should come as a right child of 20 and it's a new node. So remember, always a new node should be a red node. Yes, I have inserted. Now, if you see, there is a red-red conflict. So whenever there is a red-red conflict, then you have to do some adjustment for making it as a balanced red-black tree. So there are two approaches for adjustment. Remember this one. First one is recoloring. Second one is rotation. Now I will take some sample example here and I'll show you what does it mean by recoloring and what does it mean by rotation. Then we will continue with this one. So now we will learn those two steps, recoloring and rotation. Here I have examples. See this. This is a newly inserted node and its parent is red. This P is for parent, N is for newly inserted node. And this is grandparent. So I'll write G here. This is grandparent. And this is uncle for this node. So it means the sibling of a parent. So sibling of parent means uncle, right? So we use the term uncle here. So for a newly inserted node, its parent is red and its uncle is also red. Then what to do? Recolor the node. So how to recolor? Change these to black. So make these as black and this will remain red only. New node will remain red only and this will become black. And the parent, we should make it as red. Parent should be red. This is what you have to choose. Change the colors. So this is called as recoloring. And after that, if suppose P is a root node, then you have to make it black. So that will also become black. If it is not root node, then it will recursively, it will check upwards, that is towards the parents of P. So this is the procedure of recoloring. Just I have shown you recoloring, that you remember. Okay, how to do while creating this one, I will explain you. So don't have to worry about that. If you simply try to understand, this is confusing. Let us use it, it becomes easy and simple. Now next thing. If suppose newly inserted node is this one, red, and its parent is also red, then only you have to do something, right? If it is black, then no need to do anything. If it is red, then check uncle. I said nulls are also black. I'm not showing other nulls. The diagram looks congested. So I'm showing only this uncle. This is null. This is also black. So parent is red, but uncle is black, then you have to perform rotation. If a parent is red and uncle is also red, recolor. Parent is red, uncle is black, perform rotation. Then if you remember from AVL tree, the rotations we saw were LL, RR, LR, RL, 4 types of rotations we saw there. Yes, a similar one. We will change the names here. So this is RR. So we'll perform rotation along this one. So instead of RR, or left or right, we have a single name that we can say zigzag rotation. This is RR rotation. So this B becomes parent and A becomes left child and C becomes right child and this root remains black and these children will become red. So you have to give the colors like this. And otherwise, if this is the new node, this is parent, that is red, and its left child, that is uncle, and it is black. So parent is red, uncle is black. Then we have to perform this is RL rotation. So this is called as zigzag rotation. So zigzag rotation means RL as well as LR, and zigzag notation means LL as well as RR. So we have this name. So this is combining both the rotations. So only two things we have to take from here. What is that? Newly inserted node, if its parent is red, then check uncle. Uncle may be red, uncle may be black. If uncle is red, recolor. If uncle is black, then perform rotation. That's what. This is the point that we have to pick up from here, right? We don't have to go into details, just ignore them. When we are creating it, we can understand everything. So let us continue. So here we have red conflict. Then what is uncle here? Uncle is this node and this is black, which is null. So it means parent is red and uncle is black. This is the new node, right? So we have to perform rotation. So let us perform rotation over this grandparent. So rotations are performed over grandparent. So this is just our rotation. We know we have done this in AVL tree. So let us perform rotation and I will write on the tree here. So this 20 will come here, that will become black, and its left child, that is 10, and the right child will be 30. So this is 10 and this is 30. This is after rotation. Watch it closely, right? If you are unable to follow at any place, just pause and watch it again. And you do it on pen and paper. Just take a pen and paper and practice it also by yourself. Okay. Now let us continue. We have finished till here. Now let us insert 50. So here I will write on the top, insert 50. Where 50 should be? Start from root, search for 50. 50 is greater than 20 and greater than 30. So it should come on the right side. It's not there. So insert it. So newly inserted node 50, that will be of red color. This is the new node. Now this is the new node. This is parent and this is grandparent and this is uncle. Now there is a red conflict. As I said, if there is red conflict, then only you have to perform a recoloring or rotation. So red conflict is there. Parent is red and uncle is also red. So if parent is red and uncle is also red, means change the color. So let us change the color. So in this tree only I will modify, change the color, make this as black and this also as black and this as red. So parent and uncle as black and grandparent as red. But this grandparent is a root of a tree and root must be black. So again we have to modify this one. So especially you should check this, that root is black or not. If it is root, then keep it black. So this is after inserting 50. This is the tree. So once we saw rotation, second we saw recoloring. That's it. We have to continue like this only. Let us insert next key, that is 40. Insert 40. I'll draw this one. Here I have taken a same tree. Now insert 40. 40 is greater than 20. 40 is greater than 30. 40 is less than 50. So it should come on this side. So here I should insert 40. This is red node. Every new node is red node. This is new node and this is parent and this is grandparent and this is uncle. Uncle is black. Now if you observe, parent is red and uncle is black. So if parent is red and uncle is black, that is uncle is black, we have to perform rotation. So which rotation we should perform on this one? This is right and left based on the grandparent. So using grandparent we have to perform rotation. So it is double rotation, right? If you remember double rotation, that is a zigzag rotation we have to perform. After rotation, I will write on the tree directly here. 20 is here and 10 is here. Upon this rotation is performed. So if you perform rotation like this, then 40 will come here directly from AVL tree. If you remember, directly you do that one, right? So don't take two steps, directly do it. 40 will come at this place. So 40 is this one. Right child is 50 and the left child is 30. So this becomes 30 and this becomes 50 and grandparent remains red and these will become red. So this is after performing rotation on this one. So this is the final tree we got after rotation. Now before continuing insertion of remaining keys, let me show you the height of black. How many blacks in this path? 1, 2 and null is also there. 3. 1, 2 and null is also there. So I will draw that null also. Okay, these are black. So 1, 2, 3, 1, 2, 3 and in this direction if you go 1, 2 and this is one more black 3, 1, 2 and one more black 3, 1, 2, this is black 3, 1, 2, this is black 3. So in every direction you go, it is 3 only, it is same only. So you don't have to take a special care of maintaining number of blacks. You don't have to do. Follow this one. Follow this one. Right? If there is color conflict, either recolor or perform rotation. That's what. So you will get a red black. So I will insert remaining keys. For that I will remove this one. Next key is 60. So insert 60. So this is the final tree that I have. So in this only I will insert 60. 60 is greater than 20, greater than 40 and greater than 50. So 60 should come here. So as a right child of 50, this is 60. Now this is a newly inserted node. This is parent and this is uncle and this is grandparent. Now check this. Newly inserted node red and this is also red. Red conflict. And check uncle. Uncle is also red. If parent and uncle both are red, then what to do? Recolor. How to recolor? Modify these parents as parent as well as uncle as black. So these are black. Then grandparent as red. Now see this, interesting. From this point you see this. This is very important. Now again for grandparent, check in its ancestors. Check this one. This is parent, that is black. This is red. So red and black, it is not a conflict. If no conflict, then stop. If suppose this was also red, then you have to check upwards. So we have a tree up to here only. So this is red and this is black. So if you have red under this black, then no problem. If there is red, then we have to continue. So the thing that we learn, one more thing we learn here is that after recoloring, grandparent becomes red, then again you have to check it in its ancestors. So parent is black, so no problem, stop it. Now I will take this same tree here, I will draw it up to 60 we have finished, then I have to insert 70. So first of all I will draw the same thing there, then I will insert 70. So this is the same tree I have taken, black, black, red, black, black, red, black, black, red, black, black, red. So same thing. Now insert 70, inserting 70. 70 is greater and greater and greater and greater. So 70 comes here as a right child. So 70 will be here. See, I am trying to insert always on the right hand side. So we can come across all the possibilities here. If you do on the left side also, it's the same thing. So we are learning every possibility here. Okay. So now if you observe, there is red conflict, red conflict. This is a new node, this is parent and this is grandparent, and uncle is null, right? I am not showing null, all these are nulls, right? These are also there, null. But we are focusing on this one, so that's why I am drawing only that one. This is uncle, uncle is black. So this parent is red and uncle is black. Perform rotation around grandparent. So perform rotation around this one. So after rotation, how it looks like? This is 20 which remains same, this is 10 remains same, and this is 40, okay, and this is 30 which remains same. We have to perform rotation over 50. So at 50 comes what? 60, and left child is 50, right child is 70. This one. So grandparent was black, so it remains black only, and these children, when we perform rotation, so this 60 will become black and these children will become red. Now let us confirm whether it is balanced or not. So for that, let us count the number of blacks along the path. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. All the paths I have checked, there are all 3 black nodes, right, in this example tree. So it is balanced. Number of blacks along the path are same. So this is balance. Now till 70 I have finished. Now I have to insert 80. So I have to remove everything from the board. So if you want to take a snapshot or copy this one, you can copy it. I will take this tree once again here and I will continue the rest of the keys. So I have taken that tree here. Now we will insert 80. This is interesting. We are going to learn one new thing again here. Let us see this. Insert 80. Where it should come? 80 is greater than 20, greater than 40, greater than 60, greater than 70. So 80 should come here as a right child of 70. This is right child. Now red conflict. This is a new node. This is parent and this is uncle and this is grandparent. Red conflict is there. So check uncle color. Uncle is red. Parent is also red. Uncle is also red. Then what to do? Recolor them. Make parent and uncle as black and grandparent as red. So check this one. I will change this 50 to black color and 70 also to black color, and this is 60, that is grandparent, as red. Now remove this and consider this as a new node now, and this is parent, this is grandparent, and this is uncle. What I was saying, that when grandparent becomes red, then you have to check in its parents and ancestors also. So that's what this was recoloring. The result of recoloring, this became red. Again, there is a red conflict, red conflict. And when there is a red conflict, check uncle. Uncle is black. So for this node, parent is red, uncle is black. So perform rotation around grandparent, around grandparent. So around this grandparent we perform rotation. So we know very well from AVL trees, we have seen this. We will perform rotation in these three nodes and we'll do that rotation. So 40 will move up, 40 moves up, right? And 20 and 10 comes this side. So this is for 20 and 10 is black color as it is, right? Grandparent will become black and children will become red, right? So at 40, who will come? 60. This is 60. And its child is 70 and 80. I will copy them as it is. This is 70 and this is 80. I have taken these as it is. Now 30 is black. Where it should go? It was left child of 40. It will come on this side. So it will be right child of 20. This is 30. And what about 60 is left child? 50 is as it is. This is 50. It is black. So you can see that out of these three nodes, this has went as became a grandparent and this became red color. This is red only and this became black. So this is black, this is red and this is red only. This is the final tree. So you can see that the insertion was done here, but the rotation is performed here because there was red conflict at this point. Now confirm whether it is perfect or not. So how to know that? Count the number of blacks. So here are black, right? Nulls are also black. So count the number of blacks nodes. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2 and 3. 1, 2, 3. So along this path. 1, 2, 3. Yes, 1, 2, 3. It's balanced. So in all directions, see, I am getting 3 only every time. So don't think that always it should be 3. Don't assume this one. It depends on the height. I have few keys only. So height is small. That's why I am getting count as 3, right? So as it is going bigger, number of black nodes will increase definitely. So this is the new thing we learn. That is, first is recoloring. Second is rotation. So we have done both the things here. So newly inserted node is always leaf node. And then we have to balance the red-black tree. So till here we have finished. Now I have to insert 4 and 8. So let us do it quickly. I will insert 4. So 4 is smaller than this one and smaller than this one, smaller than 10. So 4 should come on the left of this one. Always we insert it as a red color. So 4 is red color. Check. Red conflict? No, it is black. So no need of any rotation or any adjustment. It's perfect. The next key is 8. 8 is less than 40, less than 20, less than 10, but greater than 4. So it will be added as a right child of 4. So this is 8. Now check red conflict. Yes, there is red conflict. This is new node, this is parent, this is grandparent, and this is uncle. I will remove these. This will be confusing sometimes. This is uncle. Only one null we are looking at. So uncle is black, parent is red. Perform rotation. So which rotation I should perform? See, this is zigzag rotation because this grandparent's parent, this child is left child and this is right child. So we know this is double rotation. So I should do it like this. So what will be the root? New root, this 8 will go there and 10 will come as a right child. 10 will come as a right child and 4 remains there only. This is the result. And grandparent is black and its children are red. That's all. This is balance. So we perform zigzag rotation. Rotations we know already, right? Which rotation you should perform, you can clearly see that. Okay, then whichever direction you have a red conflict, see that it is LR, RL, LL or RR. So from AVL you can borrow that. Otherwise it's difficult if you try to work in zigzag or zigzag. So it will be a new thing for you. So you can adjust yourself with the rotations of AVL tree. So I have performed like LR rotation I have performed. Now let us confirm whether it is perfect or not. Check the height. Okay, leave nulls, just count black. 1, 2. Okay, null is there. Definitely null is always there. So ignore it. 1, 2. 1, 2. 1, 2. 1, 2. So in every path we have 2 black nodes, including null, 3 black nodes. So this is the final red black tree for the keys that I have taken. So this is the procedure for creating a red black tree by maintaining all the properties we have learned. Root is black, the number of blacks along any path are equal, there are no consecutive red. And lastly, one more important thing, in this tree, whatever the height is, just you ignore reds, reds, the height will be less. So actual height is log n, but including reds, it's a double. So it's allowing us to increase up to 2 log n. So that's how the height is 2 log n. If you move reds and see it is log n, suppose, then including red, it is 2 log n because colors are red or black. Okay, if only all blacks, it is log n, only all reds, it is log n, red and black both are there, so 2 log n. So that's all about red black tree. I have shown you how to create a tree and what are the operations we have to perform, recoloring and rotations we have done, and we have learned how to generate. So you have to practice this whole thing by yourself. Do it once by yourself. Without that, you cannot remember it and you cannot do it again. So you have to do it. All those steps you do it once. Then later on you can add more keys by yourself also. That's all in this video. In the next video I will show you how it is related to 2, 3, 4 trees. And once you see that, it's become damn easy. Red black tree becomes a damn easy if you're comfortable with 2, 3, 4 trees. I'll take the same keys and I will show you how it is related to 2, 3, 4 trees. In this video, I am going to show you how red black trees are related to 2, 3, 4 trees. 2, 3, 4 trees already we have studied. We have learned how to create a tree by inserting the keys and also how to delete. So 2, 3 tree, if you have not seen, I suggest you go back and check the video on 2, 3, 4 trees. 2, 3, 4 trees. So let us see how they are related to red black tree. So here I have some examples. See, this is 2, 3, 4 tree. 2, 3, 4 means every node in a tree can have 1 key, 2 children. 2 children, that means 2. Or a node can have 2 keys and 3 children, so that is 3. Or a node can have 3 keys and 4 children, so that is 4. So that is the degree of each node, can be either 2 or 3 or 4. So the number of keys can be either 1 or 2 or 3. So I have examples of these 2, 3, 4 trees. Now here I have similar red black tree for a 2, 3, 4 tree. So let us compare them. See, this is a red black tree. There are no red nodes in this one. How it is related? See, there is a node and it is having just 1 key. And next node that is on the left side is having 10. Then one more node is having 30, that is right side of 20. So there are 3 nodes. So these are 3 nodes. And this is 20, this is 10 and this is 30. Now next, this tree if you see, first node is having 2 keys, 20 and 40. So single node is having 2 keys. So if you look here, a single node is having just 1 key as it is binary, right? So just 1 key. And this 40 is shown as red. That means 40 is inside the node with 20, just like this, Means it's a part of 20, that node 20. So red node is nothing but as a part of this node. The key is a part of this node. Then on the right side we find 10. So 10 is a new node, separate node, right? Separate node, so black color 30, separate node, so black color 50. Now third example, 20, 40, 60. So single node is having 3 keys. Middle key is a black node. And for this black node containing 20 and 60 also. So they are shown as red. So they are not in separate node in a 2, 3, 4 tree. They are inside the same node. So that's why they are having red color. So if you combine this 20 and 60 together with 40, it becomes the same node. So it means that red color nodes are related to its parent black color node. Yes. Then there are 4 nodes, separate nodes. So all are black. So these are black. Then I have one more example here. See, this is one node, black color. One node, black color 10, black color 10. 15 is also there inside the same. So that is a red color node on the right side of 10. Then one more node, 30, 40. 30 is black color. 30 is black color. 40 should be red because it's not having its own node, separate node. It's along with 30. So that's why it is a red color. Now finally we can take it as a general formula, like just look at this one. See, if there is only one key and two children, so this is one key black color and two children black color. If there are two keys and three children, so out of two keys, one key is black and this key is red and these three children are black. So if a new node is there, then it's black. If a key is within an existing node, then it is red. Then three keys are there. So this middle one is black, left side is red, right side is red, because all three together, these three together are in a single node. There are four new nodes, children nodes. So all those are black. So this is how you can take it as a general form as compared to 2, 3, 4 trees with red black trees. So you should draw this once, right? Just watching will not help you. You have to draw this once. So copy this and work out by yourself once again. Have a look at it, then do it by yourself. Alright. Now next I am going to take these keys and generate red black tree. Simultaneously I will show you 2, 3, 4 trees also. How we are inserting in red black tree, and insertion is causing recoloring or rotation, and how they are related to 2, 3, 4 trees. So let us do it for these set of keys which I already have shown in the previous example. So let us relate red black tree with 2, 3, 4 trees. So I'll remove this and do it. Let us create a red black tree for these set of keys, and simultaneously I will show you 2, 3, 4 tree. So let us insert first node. As it is a root node, 10. A new node should be a red node, but this is a root node, so it will be a black color node. So 10. Then here 10. 2, 3, 4 tree. Now next key 20. 20 is greater than this one, so it will come as a right child and it is in red color. Every new node is red color. So when a new node is inserted and if parent is black, then no problem in red black tree, right? Then this means what? It is on the right side of 10 in the same node. So 20 comes here. This is 20. Perfect. The next 30. 30 is greater than this one. 30 is greater than this one. So these two we have inserted. 30 I am inserting now. So 30 is inserted here as a red node. Now this is red conflict. Red conflict. This is a new node, right? And this is parent and this is grandparent. This is a uncle, right? So parent is red but uncle is black. So what to do? Rotate. Which rotation is required? RR rotation or left hand side rotation or zig rotation. Whatever the name you like, you can take it. So how it looks like? See, this 10 will come down, okay, and it will become red color, and 20 will move up and it will become black color, and 30 comes here, that is red color. So these are the changes. So I'm not drawing a new tree now. I'm making modifications to the same tree. Now this means 30 is inserted here. So 30 is inserted here. Already I have shown you that single node is having 3 values. So this is middle node is black and left side is red, right is red. So this means these two reds are as a part of the same node. Now next key. Next key is 50. So where it will be inserted? Here. 50. Red conflict. So what we do here, this is new node and this is parent and this is grandparent, this is uncle. This is red and uncle is also red. So what to do? Change the color of parent and uncle to black. So these two should become black. Right? And grandparent should become red. But as it is root, after making, if I make it red also, actually it's a root. So again convert it back to black. If it was not root, we would have kept it red only. This is the result after inserting 50. Okay. So we have this node and 2 new nodes, and 50 is a part of 30. Let us see how it happens in 2, 3, 4 tree. So when we want to insert 50, 50 comes here. There is no space for 50. Then what we do? We split this node. Right? Then what we can take on this side? So out of these 4, 10 will be on this side, then 30, 50 will be on that side, and the parent will contain just 20. Parent will contain 20. So if you know about this insertion in a 2, 3, 4 tree, it's better. So already I told you that if you have not seen it, just go and watch it. So splitting is done. We have done splitting, right? So 50, there was no space, so we have splitted. One node this side, two node that side, and this 20 goes up. Check it. 20 is a separate node, black color. 10 is a separate node, black color. 30 is a separate node, black color. 50 is a part of same node, red color. This is matching with 2, 3, 4 trees. The next key is 40. 40 comes where? 40 comes as a left child of 50. Now this is red conflict. This is a new node. And this is parent. And this is grandparent. And this is uncle. And parent and uncle. If you check the colors, this is red and this is black. So perform rotation. Which rotation? This is zigzag rotation or RL rotation. So what happens, as we know about the rotation, 40 goes up here, 40 goes up here, and 30 comes down as a red color node, 30, and 50 remains as a red color node. That's how it looks like. Right? So it means when we are inserting 40, where 40 should come? In between these two. When it is in between these two, just move 50 here and insert 40. Insert 40. Now what that node says? That 3 keys in a single node means what? One of them is black, middle one is black. And this left side and right side are red. Yes, left side and right side are red. So it's completely matching with that 2, 3, 4 tree. All 3 keys together in one node. So these two red says that we are part of 40. So 40 is in the middle there. That's it. Now next, after finishing 40, let us insert 60. 60 comes here. Red conflict. Red conflict. So what we did here in red conflict, this we made it as, because this is red and uncle is also red. So recolor them, make them as black and make this as red. Make this as red, 40 as red. Got it? So we want, now check this one. Is there any red conflict? No, this is red black. This is perfect. So already we know this. So this is red and this is black, so there is no conflict. So this is perfect, right? This is balanced. Now what happens here? Let us see. When I want to insert 60, there is no space for 60. Then what to do? Split that node. Okay, split. Then after splitting, what happens? When we have splitted, 40 will go up, right? And 50 and 60 will go as right child of this one, right child of 40. So this is how splitting will done. I will redraw this 30. I'll take some space here. Okay, 30. See, 30 and 40 and 50 were there. So when we want to insert 60 also, there is no space. So we split and 1 key on this side, 2 key on that side, and middle. Actually, it's not exactly middle. So right bias this is. So 40 goes up. So now what this says, see, first node, black color. 40 is a part of that, red. Black color, red. Then this is having left child, separate node, black, separate node, black. This is separate node, black. So this is separate node, black. This is 50, separate node, black, separate node, black. 60 is a part of 50. 60 is a part of 50. Now next key, that is 70. I will insert 70 now. 70 will come here, right? 70 will come as a right child of 60 and it will be red conflict. So red conflict means this is red, uncle is black. So perform rotation. So 50 comes here, okay, and 60 moves up and this becomes 70. This node is gone. This is how it's look like. Rotation is done, zigzag rotation or RR rotation. So same way, when I am inserting 70, 70 should come here. Now what that node says, there are 3 keys. Now the node belongs to 60, 50 is left and 70 is right. So all 3 in same place, 60 in the middle, this is red, saying that we belong to 60 only, same tree. Now next 80. 80 should come on the right side of 70. 80 is inserted here. Now red conflict. Red conflict. Uncle is also red. So change this to black. Black. Then what about grandparent? Should become red. Again red conflict. Red conflict. Then check uncle. Uncle is black. So perform rotation. So I will redraw it. So we have to perform rotation over these three nodes. So I will redraw it. 40 comes here. 20 is on this side. And 20 should be red. Right? 20 should be red. And this 60 should be red. 10 is on the left hand side. Okay. And 60's right side is 70. And 60's left side is 50, that is black color only. 30 was left of 40, it should come as right of 20, black color only. Then 80 is red only on the right hand side of 70. This is the final tree. Now I will show this there. I'll show this there. Now when I am inserting 80 here, there is no space. When there is no space, I have to split that one. So I will take this as it is. I'll take this as it is, 10, okay, 30, I'll split that. So splitting this one, 50 on this side, 60 we will send it upwards, and these are 70 and 80. 60 I have to take it upwards. So 60 will go here in this node. Is there any space available? Yes, 60 can comfortably fit in here. So 60 is here. This is left of 20. This is after 20 and before 40. After 40 before 60. This is after 60. This is how it looks like. Now what this tree says. First node, 3 keys. 40 is black. 40 is black. 20 and 60 are part of same node. Red. Left and right red. Left and right red. Separate node 10 black color. 10 black color. All 30, 50 and 60, 70. Sorry, this should be 30. This was 30. I made it 40. 30, 50, 70. 30, 50, 70, all black. Now 80 is along with 70. So it's red. Exactly matching. So this is how red-black trees are related to 2, 3, 4 trees. Now if you practice this once, you will never forget red-black trees. Now you don't have to memorize properties of red-black trees. You know how they are designed, you know the main idea behind them, right? So you can gather the concept once again easily if you are familiar with the 2, 3, 4 trees. That is sufficient. You can recall everything from about red-black trees also. Now remaining keys 4 and 8, you do it. So I have shown you sufficient number of keys insertion. Now you know how to create a red-black tree and how it is related to 2, 3, 4 trees. So that's all in this video. Practice this one by yourself. In this video, we'll look at deletion from red-black tree. This is a little complex topic, but I will make it very simple. This is similar to deletion from binary search tree and involving rotations or recoloring of nodes. So let us look at the method for deletion from binary search tree. So first of all, understand it perfectly. Then deletion from red-black tree is very easy. So let us understand. So already I have taken an example. This is a red-black tree, but don't see it as a red-black tree. Look at it as a binary search tree. Now how deletion happens in binary search tree? As an example, let us delete some nodes and see the cases. So in this, whatever we understand here, that will help us understanding deletion from red-black tree. So focus on this procedure for deletion from binary search tree. Let us take example. Suppose I want to delete 90. So the method for deletion from binary search tree is first of all search for 90. 90 is greater, this is greater than this, greater than this. Yes, it is found. So we delete it. This is a leaf node. So we have to simply delete it. Now next, second example. I want to delete 20. Search for 20. 20 is less than this one. Yes, it is found. Then we delete this node. Actually in binary search tree, we don't delete that node. We delete the value. Then that node is kept as it is. Some other value will take its place. Who will take the place? Either in order predecessor or in order successor. So who comes before this node in order traversal? this one. And who comes after this one? 30. So either 10 will take its place or 30 will take its place. Alright. Now you can observe one thing. The node that is deleted is 30 and that is a leaf node. So 30 will come here and this node we will delete physically. 30 is a leaf node. So one thing we can understand that whenever you delete some from binary search tree, a leaf node is deleted. Then next, I said 10 will be deleted. 10 is not a leaf node, but it is having only one child. It is not having right child. It is having left child. Yes. So when you are deleting a node from a binary search tree, either it may be a leaf node or it will have exactly one child. It will not have two children. This is the very important point. Now let us observe through some more examples. Suppose I want to delete 50. Who will take its place? First of all, we'll remove 50. 50 is the first value found. So remove 50 and its place we will bring some other node and we will delete that node. So who will come here? In order predecessor. Who is in order predecessor? Which comes before 50? 40 comes before 50. Right? Or else in order successor, who will come after 50? 60 will come. So either 40 will go in its place and or 60 will go its place. So 40 goes their place and we will delete 40, or 60 go to its place and we will delete 60. Now if you observe in this example, 60 is a leaf node, right? And 40 is not a leaf node. It is having one child, that is left child. It will not have right child. If suppose there is one child here, there is one child here, right? What it could be, it is greater than 40. So let us say 45. Then if I delete 50, who will take its place? 40 will not take its place. 45 will take its place. So that's what. So this will not be there. So when 40 is taking place means it is having left child. So finally we can say that when we are deleting from binary search tree, it will be a leaf node or it will have exactly one child. Remember this thing. Now the deletion from red-black tree depends on this only. So in red-black tree, deletion have many cases. If you refer to textbooks, some authors say there are 6 cases, some authors say there are 8 cases. I will say there are no cases. Though I have written some cases here, but don't see it as cases. Now based on the deletion procedure from binary search tree, we will try to delete from red-black tree. Now let us come to the examples. Before that, see once again, remember this, we will be working at the leaf level, that is the last level of a tree, right? We will not be working towards the root, we will be working towards leaf because this node goes there and this nodes we have to adjust. So that's why I have these examples, right? So we are working on the smaller level, right? Lowest level. Now let us see. Suppose for example, this is a red-black tree. Imagine there are other nodes are also there. Now from this, I want to delete. Which node I want to delete? This node. Whatever the value is there in that one, I want to delete that node. Then search for the key. Node is found. Delete it. And you don't have to do anything because it is a red node and it is not having any children. So this is the first thing. So whenever you are deleting anything from red-black tree and that node is red, simply delete it. You don't have to do anything. Let us see. I want to delete 30. Search for 30. 30 is found. 30 is red. Delete it. I want to delete 75. Search for 75. 75 is found. Delete it. Don't do anything. You don't have to do any changes in the red-black tree. Just delete that node. Now one more example. I want to delete 70. Who will take its place? Either in order predecessor or in order successor. Either 60 will take its place or 75 will take its place. Suppose if you are sending 75 there, then you have to delete this node. So what is the color of this node? Red. Delete it. Simply delete it. 75 goes there and you don't have to do anything. Don't have to do any adjustment at all. Okay. So if the node that you are deleting is red, then blindly delete that node. Now let us look at another example. Same thing, red node. Suppose I want to delete this node, red node, then simply delete it. It's a red node. I have shown it here. Now I am showing it on this side, right? So delete this one. Now next one. I want to delete the node. Suppose I have to delete this node and it is having one child. It is having just one child, and that child definitely it will be black, because red color node will not have red color child, it will have black color. So this is black color. So if this node is deleted, red color is going away, then simply bring this node here and it becomes black node, right? This node is gone. This node is gone. See, remember, this was having only one left child, right? Right child was not there, only one child was there. So if you are deleting a node that is a red node, then it will simply delete and its child will take its place if there is any child. And definitely that child will be black child. So from these three examples, we can understand that if there is a red node, then search it for it, and it is red, then delete it. There are no issues. Then where is the issue? If the node is black, then there is a problem. Now we are coming to the actual complex part of red-black tree. Let us make it simple and understand it. Let us see. I have another example here. So for deletion, we considered some nodes. Let us see. This is the node that is getting deleted. So I wrote it as a D, and it is having, suppose, child. Okay, this is the child, and this is the parent, and this is sibling of a node that is getting deleted. Sibling of a node that is getting deleted. Now, when the node that you are deleting is black, there is a complexity, and it's not that complex. Let us understand it. Suppose I want to delete a node that is black, right? Then check the sibling. Sibling is red. Then simply delete this node, delete the node, and perform rotation. Perform rotation. So here comes S, and here comes P, and this child is red. So that became black, and its two children became red. Perform rotation. That's all. It's simple. So what was the situation here? The node that we are deleting is black, right? And its child will take its place. Then after that, its sibling. It's a sibling. Is red. So perform rotation. It's simple. So which rotation we perform? We have performed zigzag rotation. That is RR rotation. If it was this side, we'll perform LL rotation. Okay, this is simple. This is simple. Now comes the complex cases, complex part. See this. The node we are deleting is black, right? And it is having some child, black child. That is null. And its sibling is black. See, if it was red, perform rotation, no problem. If it is black, then we have multiple choices here. What are those? We have two choices. What is that? If both the children are black, then simply change the color. So how to change the color? Sibling, you make it as red, and let these children be black only, and make the parent as black, right? And its deleted node, this has came here. That node has gone, and its child, that is null, has came here. This is how change the colors. Sibling is black, and its children are also black. So do recoloring. Change sibling to red and parent as black. Now parent was already red, so it became black, so there is no issue. Otherwise, this will continue in the parent. So that recoloring part or rotation part will continue. We don't have to go to that much complexity. So that's it. Now, one more possibility in this one. See, the node that we are deleting is this one, and it is having null, nothing is there on this side, okay? This node we are deleting, and it is black, and its sibling is also black. Yes, then what are its children? If it is having one child or two children, whatever it is having, if they are red, they are not black, then again perform rotation. Again perform rotation. So I have taken left red child. So which rotation we have to perform? Zigzag rotation we have to perform. That is, this red goes up and the parent comes here, that is red, and sibling comes here, that is black. Sorry, parent and sibling are black, and that red goes there. So this is how you have to perform the rotation. Zigzag rotation. If it is having right child, then zigzag rotation. If both the children, you have both the options, so better perform zigzag rotation. That is RR rotation. Now which rotation is performed, it depends on the which child is available, right? If for this node, if left child is there, perform zigzag. If right child is there, zigzag. If both are there, then also zigzag. So again, if you break them, these are cases again. These are cases. So I'm not breaking them. Now, one more thing. There is something called blackness, double blackness. What is that? I did not explain anything, right? I will come to it. Now let us repeat the topic again and see all the things quickly. Let us see. If I am deleting a node that is red color node, then delete it simply. Don't do anything. If I am deleting a node that is red color node, then delete it simply. Don't do anything. If I am deleting a node that is red color node and it was having a black child, then also delete it and its black child will take its place. There was no problem. Why there was no problem? Because in red black tree, the number of black nodes along any path should be same. So if you are deleting a red color node, it's not going to affect red black tree at all. That property is not affected at all. So that is the reason if the node is red, then simply delete it. So we are bothered about the number of black nodes along every path, that is black height. We are bothered about that. And the problem is when the node is black. So that's how, if the node that you are deleting is black, then there are other situations. What other situation? If a node is black, then if this is deleted, then this is already null is black. So null comes here, right? And that node that was deleted, it was black, so black height is reduced in this direction for one time. So we make this node as, say, double black. It is having more blackness. That was null, that is its own blackness, and the node that is deleted, that blackness also. So we have to adjust that blackness. So we have to adjust black height. So that is a problem here. If the node that you are deleting is black, then it will become double black, right? Its child will become double black. Then what are the possibilities and how to handle? So for when it is double black, see that sibling. If it is red, perform rotation. Next, I'll directly jump here. If the node is deleted, then this was null. See, it will be null only definitely because the nodes are leaf nodes. The nodes that are deleted are leaf nodes. Remember this. Sibling is red, definitely children will be black. Rotation. Sibling is black, children are red. Rotation. Then another case. Sibling is black, children are also black. Then recolor. So simple. Let us do it more simple once again. If the node is red, delete it. Node is red, delete it. Node is red and the child is black, definitely will be black, it will take its place. So node is red, delete it. If the node is black, then it will become double black. Then see the sibling. If it is red, rotate. If it is black and children are red, rotate. If it is black, children are also black, recolor. So this is the procedure. So if you want to break, you can break it into many cases, right? This case, second case, third case, fourth case, fifth, and again this is sixth and seventh. You can have many cases. So I have not shown them in the form of a cases. I said that the node that you are deleting is red or black. That's all. So these are the ways how nodes can be adjusted after deleting from red black tree. Now I will take a example of red black tree and delete few nodes from it. In the next video you can watch it. So let us take a red black tree and delete some nodes from it. Now let us look at deletion from red black tree. I have an example red black tree. Let us delete the nodes. So I'll take some examples and I will delete, and if required I will perform rotations or recoloring, whatever the cases is, we will see that now. First of all, let us check the black height. From the root, black 1, 2, and this null will also be black. So 3. Okay. So 1, 2, 3. So in either direction it is 3. 1, 2, and here nulls 3. 1, 2, 3. 1, 2, yes, 3. So number of blacks are same. So it's a perfectly balanced red black tree, right? The nodes are red and black. Now let us delete the node. First value I want to delete is 90. Search for 90. Start from here. 70 and 90 is greater than this. 100. 90 is less than this. 90 is greater than this. Found. It's a leaf node. It's a red node. Delete it. If this is deleted, let us check black height in this direction. If this is gone, then count the number of blacks. 1, 2, and it's null children. 3. Yes, it is 3. So there is no effect to the black height. So just delete red color node. That's all. I have not deleted. I kept it as it is. Now let us take another example. I want to delete 100. So search for 100. So 100 is greater than this one. Yes, found. Then it is having children. So when you are deleting a node, it's not a leaf node, then find out in order predecessor or in order successor and replace that one. So in order predecessor, how to find? Go to the left side and extreme right, so 90 we have, or else go to right, extreme left, so there is no extreme left, so it is 110. So either 90 or 110 can take its place. Now it's your choice, whichever one you want. So in programming, if you want to do, you can do it always on the left side, or based on the height you can do. That are different criteria you can adopt. So you can select any one. So let us send 90 at that place. So this becomes 90. Now which node I have to delete? Not that one. This node I have to delete because this is replaced there. So this node has to be deleted. What is the color? Red color. Delete it. That's all. It will not affect the black height. Check it. 1, 2 and black null 3. It's perfect. Now let us take one more example. I want to delete 110. Where is 110? It is greater. It's greater. Yes, 110 found. Then if I delete this 110, who will take its place? In order predecessor, nobody is there. In order successor, yes, 120 is there. Bring it in this place. So 120 comes here. Now which one I have to delete? 120. What is the color? Red color. Delete it. No effect in black height. 1, 2 nulls. That is 3. So this is all about red colors I have shown you. So always I was deleting the node, that was red color node getting deleted. So simply I delete it. Now let us take some black node. See what happens if we delete black node. Now I want to delete 80. Search for 80. 80 is greater than 70. 80 is less than 90. Yes, this is 80. Delete this. Who will take its place? Nobody is there to take its place. Which color node it is? Black color node. So if I delete this, then there is nothing. So this becomes null and this null becomes double black. That's what. When you delete a black color node, it becomes its null value. Definitely it will not have any child. Null will be there and that null is double black. Now we have to adjust this double blackness. So as I said that you have to check for the sibling. Who is the sibling for this one? 120. What is the color? It is also black. So if it is also black means check its children. If they are red, perform rotation. If they are black, change the color. It doesn't have any children. No, it is having null values, right? Null values. What is the color of nulls? Black. Sibling is black and its children are also black. So in this case, we recolor. Only in this case, we recolor. So how to recolor? Convert this 120 to red color. And this parent, which was already red, make it as black. That's it. So this blackness is absorbed here. Now count the number of blacks in this direction. 1, 2, 3. 1, 2, 3. Or 1, 2, 3. Yes, 3 nodes are there. So this extra blackness is taken away there by this node and that became red. This is what we do. Already I have shown you in the cases. If sibling is black, children are black, recolor. Otherwise rotation. Only that case we will do recoloring. Now let us delete one more value. I want to delete 120. Okay, delete this 120. No problem. It's red. Deleted. Check the black height. 1, 2 and this is null, right? Null. 3. Right? 1, 2, 3. 1, 2 nulls 3. So it's perfect. It's a red black tree. Now let us delete 90. Search for 90. 90 is here. Yes. And if we delete 90, there is nobody to take its place because it's a leaf node. So directly delete this one. So no node will take its place. So null will come here as it was a leaf node and it becomes double black because we have deleted black node. Now, if a black node is deleted, then you have to check the sibling. Yes, this is the sibling and this is parent. And sibling is red and its children are black. So if any one thing, sibling and its children, if anyone is red, we have to perform rotation. Yes, we have to perform rotation as this is red. Now see, here is a special case we will learn now. Perform rotation around this P, right? Because this is red. So perform rotation. So if you perform rotation, what happens? 70 comes down here. 70 comes down, right? And 40 will move up. So 40 will move up. This was red. So this 40 will become red then this 50 should go that side. So I will draw 50 here, and this 50, this child which was black, should become red. And this 60 is already red. Okay, so this is 50 and this is 60. Okay, let them be as it is. First, let us move up. So now 20 will move up. These have gone directly there, right? These have gone there. Now 20 will move up. So this is 20. And what about his children? They are red. So they will move up along with 20. So 10 comes here and 30 comes here, and they are still red in color. Now this one change is, see, this node was 40, was red, it went as red, and these are black, right, as it is. But the child of this side, when it goes there, it becomes red. This is what the special thing that we have to take care. Alright, now before dealing with this, first of all check root. 40 is red. If there are more nodes above this 40, then it's okay. But it's a root of a tree, so we know well that we have to change its color to black. It must be black. So this is black in color. Okay, first thing we did. Now, in this case, when you have performed rotation, so there may be further violation, so you have to check that one also. That's what we are learning now. So once this is added here, so this red conflict is there. So when red conflict is there, again we have to perform rotation. So which rotation it will take? This is zigzag, that is LR rotation. So what happens in LR rotation? We can directly switch this 60 here. So this is 60, and 70 will come on this side. This is red in color, so this is 70 will come on this side. Okay, so this is gone. So 60 went up, 70 come here. So when you are performing rotation with a red color sibling, then you may have to perform rotations more than one time. So even if you remember in AVL trees, for adjustment we have to perform rotations multiple times. So that's what here we have to perform rotation multiple times. So you have to take care of this if there is any further violation. So the child which was black, which went on that side, it became red. That's what we have to take care. So that's all. This is sufficient. I have shown you all possible cases by taking an example. So I suggest you practice this one by yourself once. Then it will be easy for you to remember and also to program it. Unless you do it once by yourself, you cannot recall these things. You cannot remember these things easily. So practice them once, you will remember it always. So that's all about deletion from red-black trees. In this video, I will compare deletion from a red-black tree with a deletion from 2-3-4 tree. If you have not seen 2-3-4 tree, I suggest you go back and go through the video 2-3-4 tree. Then you can understand this clearly. In one of the video already I have explained how red-black trees are related to 2-3-4 trees. So in the previous video we saw deletion, right? So now let us compare that deletion of red-black tree with the deletion of 2-3-4 tree. So I have some examples. So directly I will show you some examples. Let us look at this first example. Here it's a red-black tree. Check whether it is perfectly having black balance or not, means the number of black along the path. 1, 2, 3, 1, 2, 3, and this also 3, and 1, 2, and 3, 1, 2, 3. Yes, it is perfect. Now how the same thing is represented in 2, 3, 4 tree? So for every black node there is a separate node, and if there is a red node, red child is there, that is along with the black node inside the same black node. So it means 20 is the right child, red color child of 10, so it will be along with that 10. So let us look at here. 30 is a node. Okay, 30 is a node. Then what 50 is doing here? 50 is a red color child of 30, so it's present there. Then 10 is a node. Yes, 20 is a red color child, so 20 is along with that same 10. Then 40 is there. 40 is a separate node. 45 is a red child. 60 is a separate node. Now I have compared the red-black tree with 2-3-4 tree. Now let us delete. So I will try to delete first red color nodes. Let us say I want to delete 20. So in red-black tree, search for 20. 20 is found here. It is red color. Simply delete it. Right? So it still have same black balance. Right? Black color paths are of same number, same size. So red color nodes are directly deleted. Now check it here in 2-3-4 tree. Search for 20. 20 is less than 30. 20 is greater than 10. So delete this one. So if you delete this, nothing will happen because that node is having one key, that is 10, and that is perfect. If keys are not there in a node, node becomes empty, then you have to perform rotation in 2, 3, 4 tree for balancing it. But it is having a key. So that's how red color nodes doesn't affect 2, 3, 4 trees. So I'll write back that 20. I'll take another example. Now listen this carefully. I am deleting one node and I will show you two cases in that one. Let us see. I want to delete 30. So in red black tree, if you delete 30, then who should take its place? In order predecessor or in order successor. Either 20 should go there, 40 should go there. So if 20 goes there, 20 is red. So deletion of red will not make any difference. This 20 goes here. I am not changing this one, just I am writing below this one. So 30 is gone and 20 is there. So this 20, node 20 will be deleted. It's red color. So this is simple. Now let us see the same thing in that 2, 3, 4 tree. If I delete 30, either I should borrow, this becomes empty, vacant. So I should borrow a key from this side or this side. So from this side, if you see 20 will come up. From this side, if you see 40 will come up, right? So first I will show 20. 20 goes up. And if you delete 20 from here, then there is no problem. So that's how in red black tree also behave in the same way. Now I'll put back the things as it is. Then I'll show you another possibility like deleting 40. Now let us delete 40 from here. If I delete 40, 40 is a black color, but it is having red colored child. So 45 will come here, 45 will come here, and it will become black. So this 40, for 40, that node is gone. And 40 will be copied at this place. So once again, 30 was here, so 40 has taken its place. 40 was black, but it was having red child. So red child became black. So if you are deleting a black node and it is having red child, then red child will take its place and it will become a black node. So let us see the same thing here. If I am deleting 30, I can borrow a key from here, 20 or 40. So if I send 40, now this place is vacant, but what is the key present there? 45. So that node belongs to whom? 45, because that is the only key. So it is here in this cell, so you can just move it on this side. Right? So this node is black color node. This node is black color node. So perfect. So it's perfectly matching with 2, 3, 4 trees. So I have shown you only red color. Now let us see if you are deleting a node which is black color, then what happens? This is one example. From here I will delete 50. So first of all search for 50. 50 is this one. And if this node is deleted, then its place will be taken by null. So null becomes what? Double black. Reason? Because the node that we have deleted was black. So in its place we have double black. So what is the rule for double black? We have seen the cases. Check for the sibling. Sibling is black. Then what are its children? You have to see the children of sibling. There are no children actually. So those are nulls. And nulls are black color. Yes, sibling is black. Its children are also black. So what is the procedure? What we do in this case? If a sibling and its children both are black, then recolor. If any one of them is red, then perform rotation. So this is recoloring. So how we recolor? This we change it to red, and its parent we change it to black. That's all. Now check whether it is balanced or not. Black balance 1, 2, 3. That is null on this side. So yes, 1, 2, 3. Right? Then 1, 2, 3. That is black on this side. 1, 2. This is red. So black on this side. 3. So it's perfectly balanced. So I'll put back the things as it is. Then I will show you there in that 2, 3, 4 trees. Yeah, the tree is back. I want to delete 50. 50. See, 50 is in a separate node. If I remove this 50, then this node becomes vacant. Then what I should do? Can I borrow any key from this side or this side? No, they are also having same single key. Then what to do? Merge. Merge means which keys I should merge together. 60 I should bring here and 70 should be on its right side. So this key is merge. It is merged with the parent. So this is 60 and this is 70 in a single node. Right? This node is deleted. So same thing is happening here. When 50 is gone, then what we did? 60 came here. So it means this is black. Yes, this is black. And 70 came along with this one. So this becomes red. This became red. So the same procedure. procedure is same as 2 3 4 tree. So swapping the color is nothing but just like merging the nodes. Now one more case is remaining. Sibling is red and its children are black, or sibling is black, its children are red. Anyone in both will perform rotation. So I have two examples, and there are 2 3 4 trees. Let us do it. Suppose I want to delete 10. 10 is gone. So this is null and it becomes double black because 10 was black. Then what to do here? Perform rotation. Why? Because sibling is red and its children are black. Perform rotation along this parent, around parent. So at parent we get 40, that is black, right? And 20 comes here. And this will be 50, right? And this child, this was black, so it will become red here. So that is 30. We have already seen this, right? When the childs are being swapped, that it is coming from one side to another side of a tree. Then if it is red, it will become black. If it is black, it will become red. So this has become red. It was black. Now check the black colors. 1, 2, 3. Okay, 1, 2, 3. So in all our examples, we are getting 3. It doesn't mean that always the number of blacks will be 3, right? In our example, we have small examples. So the number of blacks are always 3 here. So 1, 2, and that null is 3. So it's perfect. So let us see what is happening in this one when 10 is gone. Can I borrow anything from here? No, I cannot borrow anything from here. Then what to do? Merge these two. So 20 comes here, 30 will be followed by that. And this 40, I should move this side. So 40 and 50 should come to this node. So we should not have blank space here. So I have just shifted them. So 20 and 30 are merged. So that's what it is happening here. With rotation also, it is merging or borrowing, whatever it is. So this is merge. So now you can see that 40 is node black, yes. 50 is a node, yes, black. And 20 is a node black. 30 is along with that, so it is red. So this is what we got. Now the last example I have, a node is black and its children are red, and I want to delete 10. Let us see that also. For this already I have this tree, right? I want to delete 10. So 10 is gone. So it is null. As the node was black, so this is black heavy, right? It is double black. Now when it is double black, check the sibling. Sibling is black. What are its children? Children are red. Here sibling was red, children were black. Their sibling is black and children are red. Just contrast to that one and the situation is same. We have to perform rotation. Then this is parent. We have to perform rotation around this one. But which rotation we will perform? We can perform zigzag rotation, that is right left rotation. We can perform right left rotation. So in right left rotation, this node will become root. 30 will move up. 20, as it is black, it will remain same. It will come on this side. 40 will remain same at its own place. And 50, that is red, it remains red. It's not disturbed at all. So this just 30 has gone up and it is root now, so it became black. So that's all. This is the rotation. So when the sibling is black and its children are red, and you can perform LR or zigzag rotation, right, when it is having both the red children. Now let us look at there. Here 10 is gone, 10 is deleted, right? Then 20 will come this side. Then who will move up? 30 will move up, right? Then this place is vacant. So this is vacant. So just move 40 and 50 this side. 40 and 50 this side. This is borrowing. So we don't have to merge. We have to borrow here. So we can do borrowing also. We can do merging also. It depends, right? If borrowing possible, we do borrowing. Now see who is root. 30, that is black. 20 is a separate node, that is black. 40 is a separate node, that is black. 50 is along with 40, so it is in red color. That's how this is matching with 2, 3, 4 trees. So red black trees are perfectly a match with 2, 3, 4 trees. They are designed keeping in mind 2, 3, 4 trees. 2, 3, 4 trees can have more than one keys. Binary trees can have just one key. So red black tree is a binary tree with one key but behaving like a 2, 3, 4 tree. So this needs practice. So you practice it once and observe the things by yourself, and this makes you perfect in this topic. So that's all in this video.